So our mathematical statement of Ampere's law looks like this. And what I said in the previous video, if you watched it, is that we will ignore this term. It was actually added by Maxwell. This is the truly Ampere's law is written by Ampere, and later Maxwell added this term, which makes the equation more universal and correct. And so there's two important things about Ampere's law. It's part of Maxwell's four equations because it captures the character or the fundamental nature of the magnetic field. Namely, that magnetic field lines close on themselves. They have no sources or sinks. They don't begin or end anywhere. They're closed loops of field. And also, it is useful for solving a few, 3 or 4 different problems, which we'll look at. So it's useful for solving those. This is much like Gauss's law. Gauss's law is really more important because it captures the character of the electric field and is useful a little bit. Some of you, I think, got the impression that Gauss's law is very useful. No, it's more important in physics because it captures the fundamental nature of the electric field more than its usefulness in solving problems. We'll see later that the Biot-Savart law, which is less fundamental in nature, is actually more useful, just like in the case of electric fields. Coulomb's law was what we actually used to solve most of our problems, not Gauss's law. And so Coulomb's law is to Biot-Savart as Gauss's law is to Ampere's law. Okay. So as you should know, mathematics is an important language or system for understanding and describing physics or physical reality. So Ampere's law is a line integral, and we've seen the line integral in first semester. So it's useful to make this connection with the physics, the mathematics, and what we previously learned. So to calculate work, we multiply a force times a distance, right? But supposing the force is varying, or supposing the path is curved. So if we apply a force like to a crate to pull it across the floor, how much work did we do? Well, the only part of the force doing the work is the horizontal component. The vertical component is perpendicular to the displacement and does no work. So that's where the dot product comes in. So when we take the force dotted into the displacement, right, that's F times ds, or delta s, if we do it in real increments, times the cosine of the angle between them. And the cosine pulls out that component, that horizontal component of the force vector. So we multiplied this component of the force vector by the amount of displacement. And if any of these quantities vary, then we have to do the integration in steps. We can either do it in small steps and get an approximation, or we can use calculus, right, to do the integral in an infinite number of steps. So let's do it. Here's a wire, and we draw a loop around the wire, and we go around the wire taking the component of B parallel to the displacement vector, and here we're showing it as a summation. So we take a little dl, the field is this way, we find the parallel component, we multiply that by the length of dl, and we continue around the loop adding up all those contributions. Well, that's really, if possible, we just use calculus. And what we see is that integral around the closed loop ends up being equal to mu naught times whatever current is enclosed in the loop. And so let's do it around this loop. What I'm going to do is, here we're integrating. We choose a path that's a circle. We center the circle on the loop, and then we do the integral, and we end up getting the value, the equation for the field due to a current carrying wire. So I'm going to show you. I'm going to actually do this in a little detail. Let me pause and set that up. So we're looking at a wire with current coming out of the screen, out of the page at us. That's the circle and the dot. So the current's coming out. We use right-hand rule number 2. We point our thumb out of the page and our fingers curl counterclockwise. So these are circles. I haven't drawn it perfectly, but these are concentric circles where the field gets weaker and weaker the further we get away from the wire, but the field lines are always closed loops, circular on the wire and centered on the wire. So we want to do this integral of b dot ds, and so we draw a loop. So we could draw a square, we could draw some weird shape, but no, let's make it easy on ourselves. Let's draw a circle which is concentric on the wire. So I've drawn the green circle. That's just a circle that I drew. It's my Amperian loop. Whoops, I need to have a little circle there because you have to be a closed loop that we're going to integrate around. And I'm going to do the integral around that closed green loop that I chose, my Amperian loop, and I'm going to do this integral. And so that's b times ds times the cosine of the angle. So let's do that. Let's pick a little ds. Here's a section. So here's a ds. And we're going to go counterclockwise. Why? Because that's the direction the field is going in. We can do it in any direction we want. And we see that it's so simple, it's almost hard to see. For every ds that I choose, because it's a wire and the field is circular, the ds will always be parallel with the field. And so because the wire is long, any point at a given distance a, let's just say that this green loop has a radius I'm going to call a. So now any place on the loop, that field, even though we don't know what it is, the field is going to be constant. So we can pull the field out of the integral. We can say, oh, b is a constant over that loop. And so all we have to do is integrate over the circle, ds, and by Ampere's law it'll be equal to mu naught I enclosed. And so the ds, if we integrate every piece along this loop, what do we get? We add up all those ds's, we're going to get the circumference of the loop. So what we have is b times the integral of all the ds's, the circumference of the loop, 2 pi a, and that's equal to mu naught I. And so when I do the algebra, I get b equals mu naught I in the wire over 2 pi a. And so we just use Ampere's law to derive this equation, which we have been using and will continue to use to find the field around a current carrying wire at any point a distance a from the wire itself. So that's the first, simplest, and very useful application of Ampere's law. So remember, Ampere's law is important because it captures mathematically the fundamental nature of magnetic fields. But in a practical sense, it's useful in 4 situations, and we just did the first one. The second one is there a magnetic field inside the wire? Supposing we're inside the wire, how do we get the magnetic field of a long current carrying wire? We'll use Ampere's law to do that. And it's also useful for finding the field inside a coil of wire. And the last application is the field inside a donut or toroidal coil of wire. So those are the 4 applications when it can be used to derive expressions. And these are all important, especially this one, which we have, the B equals mu naught I L N over L. So let me walk through those one at a time. Let's do this one next. So here's a diagram of a expanded, enlarged wire. And we did this. We found the field outside the wire. And as long as the wire is cylindrical, this result will be good. But now we want to find the field in here. So I'm going to draw a diagram to help us do that. Okay, here's our enlarged wire. And I changed the direction of the current, so it's now going into the page. And I'm showing the field, not perfectly drawn, but circles concentric around the wire. So the blue lines are the magnetic field. They're going around in the direction, in a clockwise direction, because I changed the direction of the current. And then I drew a green Amperian loop inside the wire. So when I integrate around this wire, I'm going to argue the same thing. I'm going to argue that any ds that I choose is going to be parallel to the field because of the symmetry. The field should be, if there is a field, it should be circular inside the wire. And so when I do the integral of b dot ds, so similar to the last one we did, the b, whatever it is, as we go around the green loop, is going to be constant. So the b can be taken out. Whatever the value is, we don't know what it is, but we know that it will be constant over that loop by the symmetry of the situation. And when I integrate the ds, I get the circumference of that green circle. So I have b times 2 pi a, where a is the radius of that green circle, and that's equal to mu naught times I enclosed. Only notice that the green circle does not enclose all the I, so we have to figure out how much I is enclosed in that circle. So the I enclosed in the circle is going to be the total I times the area of the green circle, pi a squared, over the area of the outer circle, or the entire wire. And so that's pi r squared, where r is the radius of the wire. Right? That's the area of those 2 circles. So the smaller a is, the less surface area. The current through the loop is going to be proportional to that ratio of surface areas. I hope you can see that. Now doing the algebra, crossing out the pi and the a, crossing out pi and one of the a's, and dividing through by 2, we get that b equals mu naught I a over 2 pi r squared. Okay, does that make any sense? So this is what we do. Let's look at it and see if it stands up to what we might expect. So 2 things you might do is let a go to 0. If a goes to 0, that green circle shrinks to 0. And at the center of the wire, that would be at the center of the wire. So as you get closer and closer to the center of the wire, the field gets smaller and smaller and goes to 0. That makes sense. And the other check would be, supposing a we expand the green circle till it matches the outer part of the wire. We let A equal R, and if A were equal to R, then we have mu naught I R over 2 pi R squared. That would be mu naught I over 2 pi R, which is exactly the result we got for being at the surface or outside the wire. So that all makes sense. So our result looks good. This gives us the field inside a current carrying wire where the current is evenly distributed over the wire. Okay, let's do the coil. So when you first look at the coil, you might think, how am I going to draw an Amperian loop that matches that symmetry? But watch this trick. So the loop that we're going to draw is this black line. So notice that the black line is a rectangle, and there are 4 segments. And so the first segment, A to B, is just parallel to the field. Then we turn 90 degrees, and as we go in this direction to make our rectangle, you'll notice that this line is always perpendicular to the field, which is along X, because this is along Y. And as we go along Y, the field, even outside, is weak and also pretty much along X as it bends back. And so the integral along this side will be 0. The integral along this side will be 0. And if we take it far away, as we integrate across, the field far away will be close to 0. So we can easily claim that the integral along these 3 sides adds to 0. So the total integral of B dot ds around the closed loop is just the integral over this one side. So let's do that. So the integral from A to B of B s ds cosine theta equals mu naught over I enclosed. So the B is constant over that, right? The B is constant. It comes out of the integral. Cosine of theta during that whole segment, theta is going to be 0. The field and the displacement vector are parallel to each other, and so the cosine is 1. And so all we have to do is integrate all the ds's from A to B, and that will be the length of that segment, L. So out of this we get B times L, and that's equal to mu naught times I enclosed, but I enclosed will be the total number of wires in this square, in this rectangle, and so we'll call that total number, whatever it is, N times I. And when we divide both sides by L, we get the result that B equals mu naught N over L times I, where N in this case is the number in this length L, but since the winding density is uniform over the whole coil, the N could be the total number of windings and the L the total length of the wire. And so we can also write this alternatively as B equals mu naught N, which is the winding density, times I. Those are the 2 forms of the equation on our equation sheet for the coil of wire, and there you have it. So let's finish with the toroid. The toroid is a very interesting form or device in electric circuits. It's a coil, it closes on itself. And so since it closes on itself, the magnetic field lines inside the coil can close on themselves. And so it's a device that has no magnetic field outside it. All the magnetic field is contained within it. And so we want to know what is the strength of the field within it. So the figure shows we have a toroid with an inner radius A and an outer radius B, and we pick any R we want, as long as it's bigger than A and smaller than R, and we draw a circle. Because from the symmetry, it's obvious that whatever magnetic field is in there is going to be circular. So now we just need to do our integral. So once again, we integrate over that blue circle. And since the field inside is going to be circular, the cosine of the angle that is the angle between the ds and the b, is going to be 0 degrees. So the cosine is 1. B will be constant over that blue circle because we're the same distance from the edges of the coil. And so all we got to do is integrate all the ds's, and that's the circumference of that circle. So this integral ends up being b 2 pi r, which r is the radius of the blue loop. And that's equal to mu naught I enclosed, and in this case that blue circle encloses every single winding. Look at it, it encloses every single winding of the coil. So in this case it's mu naught times the total number of windings times I, the current in the coil, and so we get the result that B for the toroid is mu naught N I, the total number of windings, divided by 2 pi r. So it does depend on r. So does that make sense? As r gets smaller, the field will get bigger. So the field in the inner part of the toroid will be bigger than the outer part. But if the A and the B are large, that variation in r, the variation in field from the inner surface to the outer surface, may not be very great. But anyway, that's the result of the coil. That's the fourth application of Ampere's law, deriving practical, workable physics equations. And we're done.